Okay, 2-4, day 1. We are going to look at continuous functions, the calculus version. As far as continuous functions go, back in junior high, they probably taught you they were continuous if you could draw the whole thing without picking up your pencil. So we'll go with that definition to start with. So a continuous function can be drawn without picking up the pencil. Without picking up the pencil. If the graph has any holes, asymptotes, or jumps, then it's a discontinuous graph. So those are the 3 things that will make any function discontinuous: hole, asymptote, or a jump. So we're just going to analyze some graphs. A big portion of your assignment is going to be given some conditions, sketch a graph with those conditions. So first, let's just analyze and see if they're continuous or not. So our first one looks like this. And we're going to ask if it's continuous at a specific point. Obviously, the point I'm going to ask here is at C. So, because I cannot draw this completely without picking up my pencil, it's a discontinuous graph. So we're going to say not continuous. And you know we're describing the discontinuity as a removable discontinuity. Because you know from the previous sections that if you've got a hole in a graph, you can factor the top and bottom of your fraction and cancel it off, and it fills in that hole. So anytime you have a hole, it's removable by factoring. Removable discontinuity by factoring. And the last thing, we want to look at, does this have a limit at C? Remember, limits the y value. Do I approach the same y value from the left and the right? And I absolutely do. So this has a limit as x approaches C. And on my graph, I've labeled it as A. All right. Just analyzing graphs, talking about the important parts. Here's the next one. Very similar. Hole in the graph. Put a point above that hole up here. Okay. B. This is the C that we're going to be looking at. So, is this continuous? Absolutely not. When I draw it, I got to pick up my pencil, continue that way, and I got to pick up my pencil to come back here. So it is not continuous. This discontinuity is removable. And does it have a limit as we approach C? Am I approaching the same y value? A single y value? Absolutely. I never actually get to the C, so I never jump up there, but I do approach the A. bit different graph. Obviously, let's see, C, A, B. This is not continuous. This is called a step discontinuity for obvious reasons. I think I referred to it as a jump up in those directions, but it's called a step discontinuity. This is not removable. And does this have a limit as I approach C? Let's see. Nope, my fingers are never going to touch. From the right, it's approaching B. From the left, it's approaching A. So there is no limit here. A couple more graphs to look at. This time, this is going to be my C value. And here's my two-part function. Okay. If you remember, that line that both sides of the function approach and get closer and closer and closer to, but never actually touch, that's your asymptote. Is this graph continuous? Absolutely not. This an asymptote is never removable. Only the hole in the graph is. And will this have a limit? Think about it. As my fingers approach the C value, they just keep going up and up and up and up and up. They never approach a single Y value. They never stop. So there's no limit here. At least we're going to say that for now. And the last one. We've got a graph that starts out kind of parabolic, hits a point, kicks back down. Okay, this sharp point here is called a cusp. And it is a point, it's filled in. They just describe a cusp as any sharp change in direction. You can see we were going up, 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 hit a point, come right back down. So it's a sharp change, up to down, real quick. Okay, and we're going to put our C value right at that cusp, and our Y value right at the cusp. So is this continuous? Let's see, can I draw through C without picking up my pencil? Absolutely, this is continuous, finally one. And we don't have to talk about removing a discontinuity because there's not one there. Does this have a limit as I approach C? You got to ask yourself, do I approach a single Y value? Are my fingers going to touch when I get to C or close to C? Absolutely. A again. So, we talked a lot about continuous and discontinuities. Now we want the calculus definition of continuity. So, the calculus continuity definition. So we don't get to continue on with that junior high, draw it without picking up your pencil definition. Okay, this definition, you will have to know all three parts of this. It says function f is continuous at x equals c, so we're always looking at continuity at a specific point, if and only if these three things happen. One is that f of c exists. That means there's a point on the graph at c. All right. The second thing is that the limit as x approaches c of your function also exists. So your two fingers will come together at a y value. And then the third part of the definition says that these two things have to be the same. So the point, the f of c, the y value, f of c, has to equal the limit as x approaches c. So our last graph, if we look at it, does f of c exist here? Yeah, it's equal to this point at A. CA would be the chorded pair. So it has a point at A. And then it has a limit. The limit also equals A. So because the point and the limit are at the same y value, that's this last part here, all three parts of this continuity definition are met, making this graph continuous. So in the next set of examples, I'm going to ask, are they continuous or not at a c value? And if you say no, you're going to have to tell me which part of this definition doesn't work for us. So, I'm going to keep that handy. Okay, so the question is, continuous at x equals c? If not, explain. And your explanation has to go back to those three parts of the definition, or at least one of the three parts. My first one. So the c value is going to be right here. Okay, so is it continuous? You can still think about that definition of, oh, can I draw it with my pencil completely? And the answer is no. So you can answer no, it's not continuous. But now you have to be able to go back to that three-part definition and tell me which part doesn't work for us. And start with the first part. Does f of c exist? In other words, is there a point on the graph when x is c? And if you look, there's a big old hole there, there's no point. So the very first part of the definition is what fails. F of c does not exist. So it can't be continuous. I don't have to look any farther. That's enough of an explanation. Try another one. Line with a hole in it. We're going to put a point here, and we're going to put C right there. So, is that continuous at C? Absolutely not.